What's up, everyone? Hope you guys are having a great day so far. It's Ben, and today we're going to be covering limits as x approaches infinity. And this is a very important concept to understand in Calculus 1 because infinity is a very new concept for you guys. It's not a very intuitive concept. It's a little bit of a blurry area, a little gray area for a lot of students because there's not many things in life that are infinity, right? Infinity is just a concept. It's something that's arbitrarily large, right? It's just something that goes on forever to very, very big, or if it's negative infinity, it's something very, very small, right? And so when we work with limits approaching infinity, it's basically the same thing that we'll do when we do normal limits as x approaches a finite number, but there's a little bit of different ways to solve these problems, different way to look at them, evaluate them when the limit is approaching infinity or negative infinity. So I'm going to be covering a few examples showing different cases of what you'll see in your classes for your homework, your test, and other things like that. So this is the first example we're going to start off with, the limit as x approaches infinity of the function 7x to the fourth power minus 3x cubed minus 4x squared minus 6. A lot of minuses, I know. That's not important. So right off the bat, this is a very easy example, right? So when we have a polynomial like this, right? Polynomials are the easiest cases that we'll have. Reason being is, which I'll show you right now, we can just go ahead and just do direct substitution, right? We can go ahead and just plug in this infinity into all of our x's, and we can go ahead and see what happens from there. So yeah, let's go ahead and do it, right? So if we just go ahead and plug this in, we get 7 times infinity to the fourth power minus 3 times infinity cubed minus 4 times infinity squared minus 6, right? This is nothing special, right? If we try to evaluate this, right, what's infinity to the fourth power? It's just very large, it's just infinity to the fourth power. It's just something very, very large. And these coefficients don't really matter. Timing it by 7 is not going to do anything. It's just another large number, it's just infinity. Here we have another infinity minus 6. The 6 is not going to do anything. Subtracting 6 by humongous numbers, not going to do anything. So we can go ahead, and when we have this case, we can go ahead and just say that our limit is infinity. It's just going to go off forever, never going to stop, never going to reach a finite number. And a very easy example, polynomials are the easiest things you can deal with when we're working with limits as x approaches infinity. And one more case is that if we're approaching negative infinity, if our limit was negative infinity like this, sorry my friends, what am I doing? If our limit was approaching negative infinity, this wouldn't make a difference because we're just going to be going to a negative infinity, right? This would just be a negative infinity. It's still infinity, just a very, very small number instead of a very, very big number. We have a very, very small. So that's a very easy case as well. So let's go ahead and get into some more challenging problems. But before we get into that challenging problems, I wanted to explain a little bit of the intuition behind this, a little bit of reasoning why it's infinity when we have polynomials like this, because yeah, so let's get right into that. So a general rule of thumb, when we have a limit as x approaches infinity of a polynomial, I'm going to denote that as p of x. That's just the way I'm going to call p of x is just any polynomial, right? When we have a limit as x approaches infinity of any polynomial, it's always going to be infinity. And it goes for the same thing if we had a limit as x approaches negative infinity of some polynomial, it's just going to go to infinity. It might vary from case to case if we have a certain, like a square or a cube, something like that, but most of the time it's just going to be infinity, negative infinity. Nothing to worry about too much because you won't really be seeing these types of problems on your exams and stuff like that. It's just way too easy of an answer. From all the tests I've seen, you won't ever have this. Maybe on your homework, but on tests, you won't ever see easy examples like this. So that's something very important. And one more thing I wanted to show is kind of show this, but graphically, right? Geometrically. So if we have a graph, right? And let's go ahead and draw the graph of our function is going to be x cubed, right? That function looks something like this, right? This is our x cubed, and this is the x-axis, it's the y-axis, right? And so say we were taking the limit, say we were doing the limit as x goes to infinity of, x cubed. To understand this graphically, we're gonna look at our function, and we're gonna go down the x-axis in the large X direction, and we're gonna see how our function behaves, right? So if we just stay on our graph, and we just go in the positive X direction, staying on our line, what Y value are we approaching? Not a very straight line, but we're not gonna approach a Y value, right? We're gonna keep going off into infinity. We're not approaching like any of these Y values. We're just gonna keep going forever. And recall that our answers when we solve limits, that's a Y value. So if our answer to our limit was 3, that's the Y value we're approaching. So are we approaching a Y value here as we go to infinity? No. And it's the same thing for any other polynomial. If it was like a polynomial, like if we had like a minus x squared, it's not gonna change the graph really, or it's gonna change the graph, but limit wise, no. It's just gonna shift the graph up and down, stretch it, shrink it. All polynomials are just gonna go off into infinity. Like if we had a parabola like this, we're just gonna keep going off in that direction. If we had an upside down parabola, we're gonna go that direction, or negative infinity, depending on what our case is. But the point I'm trying to get across is that when we're working with polynomials and limits to infinity, it's just always gonna be infinity or negative infinity. So enough of that yapping, that boring stuff. Let's go ahead and get into some more examples, some things that will actually really help you within your classes. Okay, so here we have our next example as the limit as x approaches infinity of the function 8 minus 3x squared all over 9x squared plus 5x. Now this is a great example. You really want to pay attention for this one because this is really the bread and butter of limits as x approaches infinity. Most of the time you're going to be working with rational functions like this because this is where the interesting stuff happens with infinities. We have asymptotes, we have vertical asymptotes, horizontal asymptotes, and stuff like that. And so those are very important things we need to take into account here. And so yeah, let's get straight into it. So the first thing you might want to try doing that you would probably think of trying to do is plugging in infinity into our function, right? Just direct substitution. If we go ahead and just try direct substitution right off the bat here, because that might be the first thing you might think of doing, is, well, we can go ahead and just try that out and see what we get. So you can kind of see right off the bat, we just have a whole bunch of infinities, which we don't really like. And this answer is just gonna clearly be infinity, right? We have 8 minus infinity over infinity squared plus infinity. Like it's just infinity, infinity, infinity. It's gonna approach infinity. And yes, for the last example of polynomials, our answer was just infinity. We couldn't do anything to make a different answer with polynomials. No matter what you do, it'll be infinity. But with rational functions, it's different. So we did get an answer as infinity, but there is something you need to look out for before you just leave this as your answer. Sometimes it might be infinity, but let's go ahead and try some other things out to see if we can actually get a finite value, not just infinity. So let's go ahead and try some things out. So I'm gonna go ahead and show you the longer way of solving these, and then after I'll show you a shortcut, which will make your life 10 times easier. So when you have rational functions like this, the best idea is to divide every single term by the highest degree. Highest degree is your power. All x's are just to the power of 1. If they don't have a number, it's just, you can just assume it to be power of 1. Here, we don't have any power. So we want to look for our highest degree in our function. So right off the bat, we have x squared, we have another x squared. So like I said, divide everything by the highest power. So let's go ahead and try that. So we have the limit as x goes to infinity, and I want to divide everything by x squared. So we have 8 over x squared minus 3x squared over x squared all over 9x squared over x squared plus 5x over x squared. And yes, I know this looks ugly, this looks intimidating, but it's not as bad as it looks. So what we're gonna do, we can go ahead and see if what cancels out here. There's a lot of things that can cancel out here. We can simplify it, right? So for this 8 over x squared, we can't really cancel that. But here, look, we have x squared over x squared. I'm gonna cancel these. Beautiful. Here, x squared over x squared, cancel. here we have x over x squared. This x is gonna cancel, and one of these x's down here will cancel. So after simplifying this, we're gonna go ahead and get the limit as x approaches infinity of 8 over x squared minus just 3, because that's all we're left with, over 9 plus 5 over x. So it looks like what the heck is this? We have a crazy looking function. We have fractions over fractions. Like, we don't like that. But this is great. This is very important to take note of. We have fractions here, right? And so now this is the right time to do direct substitution. And I'll go ahead and do it, and I'll show you why this works. So let's go ahead and continue this way. So go ahead and plugging in our infinity into all of our x's, we'll see what happens. So we have 8 over infinity minus 3 all over 9 plus 5 over infinity. And so this is actually a great answer, because this 8 over infinity and 5 over infinity actually turn to 0. This is going to turn to 0. This turns to 0. Because if we have a number and we divide it by a humongous number, it's going to tend to 0. For example, if we have 1 over 1 million, right? 6 zeros. That's 1 millionth, right? Very small number. If this is 1 billion, it's even a smaller number. Quadrillion, even a smaller number. So infinity goes on forever. So what are we approaching? We're approaching 0. And as infinity gets bigger, bigger denominator, smaller number, right? If we have, this is splitting up 1 into smaller parts. If we have infinity parts, the parts are going to be super small, infinitesimally small. So we can go ahead and just identify any number constant over infinity to just be 0. Whenever we have a number over infinity, we can go ahead and just, when it's a limit approaching infinity, we can go ahead and just call that 0. So continuing here, all we're left with, so if this is 0 and that's 0, what are we left with? We have just a minus 3 over 9. And that's our answer. We can go ahead and simplify this to just negative 1/3. And that's gonna be our answer for our limit. Our limit, as this whole thing right here approaches negative 1/3. And that's very satisfying, right? With infinities, when we have rational functions, we need to pay very close attention if we see if we can factor stuff out. And yeah, this is a very good example here. This is something very important to take note of as well, that whenever you have a constant over infinity, it's going to be 0, because it makes pretty intuitive sense. I'd invite you to go ahead and search up if it doesn't make sense to you. Go ahead and just do a quick search online. Why does that make sense? Where does that come from? Why is it 0? But yeah, that was a very great example. I'm gonna go ahead and show you guys the shortcut for this now. Show you why, instead of dividing everything by the highest power, I'm gonna go ahead and give you a quicker tip to solve these faster and recognize these faster. Instead of doing all this algebra, there's a quicker solution. Okay, and for the shortcut, we're gonna go ahead and look at the same example, but instead of dividing everything by the highest degree, what we're gonna do is look at the degree of the numerator and the denominator. And whether or not, what degree is higher, the numerator or the denominator, will have different results. And I'll go ahead and give you a little short bullet point list or a little quick review on what happens to the limit, what's the behavior of them, depending on the degrees on the numerator and denominator. So in this case, right, we want to look at the numerator and denominator. Highest degree on the numerator, this has a degree of 0. Here we have 2. Here we have 2. Here we have 1. And look, the highest degree on the numerator and the denominator match, which is a good thing. This is very satisfying. So now that they match, you want to go ahead and look at the coefficients. And coefficients are just the numbers that are stuck in front of a variable, right? The coefficient here is 9, coefficient there is 3. So we're gonna go ahead and take a look at our highest degree, and then just taking the leading coefficients, the ratio of them is our limit. So just looking at this is not equal, but I'm gonna write an arrow. So we have negative 3x squared over 9x squared, right? Looking at the coefficients, we just have negative 3 over 9. And then simplifying this like in the last one, we have negative 1/3. And that's our limit. That's our limit. So when we have rational functions like this, always look at the degree of the numerator and the denominator, and you can tell right away what the behavior of the limit is going to be. So that's very nice. I'm gonna go ahead and show you a few more examples of what happens when we have a numerator that's greater or denominator that's greater. So now for this next example, the limit as x approaches infinity of x to the 6th power minus 4 to the 5th all over 2x to the 7th minus 3x. And so for this case, right, we're gonna go ahead and identify the degrees on the numerator and on the denominator, right? So here, the highest degree, right, is 6. The highest degree on the bottom, 7. And so for this case, when the degree of the numerator is less than the degree on the denominator, the limit as x approaches infinity is gonna go to, it's gonna go to 0. Sorry about that, it's gonna go to 0. And that's a very easy rule of thumb to follow. And I'll go ahead and show you really quickly why. It's kind of like the first example I showed you, or one of the examples I showed you, where we divided everything by the highest power. That's exactly what's gonna happen here. So if we divide everything by the highest power, right? So if we have the limit as x goes to infinity, dividing everything by the highest power, x to the 7th, right? We have x to the 6th over x to the 7th minus 4x to the 5th over x to the 7th all over 2x to the 7th over x to the 7th, being repetitive, 3x over x to the 7th. And then, right, this is gonna cancel, one of these is gonna cancel, this, two of these are gonna cancel, these cancel, and like that, right? And so, moving forward, we have the limit as x goes to infinity, and then this is gonna turn to 1 over x. This one's gonna turn to it's gonna be minus 4 over x squared, and then this is gonna be 2, and we have minus 3 over x to the 6th. And then doing direct substitution here, we can see that this is gonna turn to 0. Remember, a number over x, as x goes to infinity, is gonna be 0. So that's gonna go to 0. So we have, when we plug in infinity, right, we get 0. This, another a constant over an x, or x squared, doesn't matter. That's gonna be 0. And then we have just 2 minus 0. So the numerator is obviously 0. Down here it's 2, but then 0 divided by any number besides 0, 0 divided by any constant is just gonna be a big ol' 0. And so that's the answer. So when we have, remember, this is just the steps on how to do it, but this is a good thing to take notes of, that when the degree of the numerator is less than the degree of the denominator, the limit is gonna go to 0. So I recommend, yes, take note on this. Very, very important. Okay, so for our last example, we have the limit as x goes to infinity of the function x plus 6 all over the square root of 2x squared plus 7. And this is a very similar example, but the square root will play a big part in this limit. So here, we're gonna go ahead and just do what we usually do. First step, just see if direct substitution works or anything. Most of the time it doesn't, but plugging in infinity here, we get infinity over infinity, infinity. So that doesn't work, so we don't like that. So let's go ahead and try something else, see if we can get a different answer out of this instead of this infinity, right? So let's go ahead and we're gonna look at the degrees of the numerator and the denominator and see what the difference is, see if they're the same, different, and we can go ahead and look at, recognize the behavior of this limit from that. And so up here, our highest degree, remember, it's 1, and down here, we don't really, you can't, as a student, you might not really know right away. So we have a squared, but we have a square root. So you might be like, is it the highest power 2? Is it 1? We can go ahead and figure that out right away, just from doing a little bit of algebra. So what we're gonna go ahead and do down here, let's go ahead and pull this to the side. We have the square root of 2x squared plus 7. So if we factor out the highest power out of this, obviously the highest power is x squared. If we factor that out, we get x squared times whatever we have left, 2 plus, and since we don't have an x in this part, in the 7, we have to go ahead and divide it by x squared, right? Because if we FOIL this back in, it needs to look the same as this. So if we do x squared times 2, we get 2x squared. If we have x squared times 7 over x squared, these two will cancel out, leaving us with 7. So that's how you know you factored it right. If it's just a constant, you're going to go ahead and pull out an x squared, and you have to divide by x squared. If it's a different x, if it was just one x, you would just put x. Or yeah, you'll have to see from there. I can't think in my head. But yeah, so pull out x like that, x squared. And then we can go ahead and take the square root of this and this separately, because with square root laws, you just do this, square root of this. So I'm gonna go ahead and show you guys real quick. This is the same thing as this. That's square root laws or whatever root law. So here we're going to take the square root of this, square root of that. So square root of x squared, you might think it's just x, but when we're working with infinities, square root of x squared is equal to the absolute value of x. And absolute value of x, because any number they plug into this will come out positive, always. So we can go ahead, that's not super important. Most teachers won't really care about that. It's not super important, but this can just be written as absolute value of x. And over here, we still have 2 plus 7 over x squared. So now we go ahead and rewrite this denominator as this. So limit as x approaches infinity of x to the power is x plus 6 over absolute value of x times the square root of 2 plus 7 over x squared. Now, so x squared, absolute value of x, when we have limits approaching infinity, if it's positive infinity, this absolute value of x, we can just assume it to be just a positive x, right? If we're going in the positive x direction, this x is gonna be a positive number, right? It's not gonna be a negative x. If we're going in the positive x direction, it's not gonna be negative. So we can go ahead and just drop the absolute value bars. I wanted to show you guys that just in case your professors care about that, but most of the time, you can just cancel out the square roots. But that's something important that I would recommend taking note of. So now here, we can go ahead and factor out an x out of this top part. So I'm moving down here just to make some space. If we have x plus 6, just like what we did in this last part, we can factor out the highest degree. So then we're gonna get x, and then this just turns to 1. Here, factoring out an x, we get 6 over x, right? Because if you FOIL it back in, you should get the same. So now, we're almost done with the limit as x approaches infinity, and your professors are probably always gonna want you to write limit every single time you write an equal sign, because you haven't actually taken the limit yet. So we have limit as x goes to infinity of x times 1 plus 6 over x all over x times the square root of 2 plus, 7 over x squared, right? So it's looking pretty good. Here, look, we have an x that we can cancel out. Nicely done. And now we can go ahead, since this is an example that we've worked with before, we can go ahead and just evaluate, we can go ahead and do direct substitution now, right? Because this should turn to 0, that should turn to 0. So let's go ahead and do that real quick. So now, plugging in infinity, we get 1 plus 6 over infinity, remember, 6 over infinity, plus, we have the big square root here still, 2 plus 7 over infinity squared. And remember, constants over infinity, when we're working with limits, is just 0. So this was 1 over the square root of 2. And that's our final answer. That was a little more tricky with square roots. If you've never had a lot of students, beginner students in Calculus 1 especially, are not very familiar with square roots. But I recommend getting good with them because they won't be leaving anytime soon. So yeah, that's gonna go ahead and be the last example of the video. I hope you guys really enjoyed. Make sure to follow. I know it's a little bit echoey. I'm gonna try to work on getting a mic soon. But I hope you guys enjoyed this video, and I hope you guys enjoyed the whiteboard content instead of being online. I prefer it this way. I'm gonna try to get in here as much as I can. But yeah, thank you guys for watching. Subscribe, leave a comment, and have a good one.